Hello, everyone. Sorry for the delay in the beginning. We have more than 500 people attending the seminar, so it takes a bit of time to get everyone logged in. So we gave everyone 2 minutes to get started. Welcome to the highlight seminar at the Andlinger Center for Energy and the Environment at Princeton University. Our distinguished guest today is ITER Organization Director-General Bernard Bigot. The chief goal of Andlinger Center is to translate fundamental knowledge into practical solutions that enable sustainable energy production and the protection of the environment. We believe fusion is an integral part of the solution. This is why we're incredibly grateful that Dr. Bigot accepted our invitation to speak today. Initially, Dr. Bigot was scheduled to give this seminar in person. We are thankful that this online presentation now allows us to have a much broader audience which have interest in the development of ITER. I will briefly give an introduction to the center and PPL before passing the presentation to Professor Steve Cowley. The Andlinger Center brings more than 100 faculty members across many departments at Princeton University, with 10 core faculty focusing its efforts on broad research areas as shown in the slide. Our programs include Distinguished Postdoctoral Fellow Program and a Visiting Fellow Program, which seeks to expand collaboration into academia, national labs, and industry. Princeton Plasma Physics Laboratory is a U.S. Department of Energy national lab for focusing on plasma physics and nuclear fusion. PPPL is operated by Princeton University, it's shown on the left, and it is finalizing the National Spherical Torus Experiment Upgrade Project right now, it's shown on the right, and contributes substantially to the efforts to make ITER Project a reality with both engineering and science collaborations. Without further ado, I will pass the presentation over to Professor Steve Cowley, who's the director of PPPL. He will have the honor of introducing Dr. Bigot. Thank you.
Thank you very much, Egeman, and welcome everybody to this seminar. It gives me enormous pleasure to introduce Dr. Bernard Bigot, the Director General of ITER. ITER is probably, and certainly I think so, the most important experiment of the 21st century. It is an astonishing experiment in its scale and its intent. And it brings together 7 partners from around the world and more than half the world's population. It is just extraordinary organization, extraordinary science, extraordinary engineering. And it's been led since 2015 by Dr. Bigot. Bernard is a distinguished chemist, material scientist who began his career as a scientist, but for most of the time that well, certainly all the time I've known Bernard, he's been a leading figure in French science and in world science. He was the High Commissioner for Atomic Energy for France from 2003 to 2009, and from 2009 till 2015, he was chair and chief executive of the French CEA, which is the French organization that leads alternative energy and atomic energy in France, and more than half really of French science. So tremendous responsibility and a tremendous leader there. And we were all incredibly grateful when Bernard agreed to be Director General of ITER in 2015, because he has really begun to make this project come to life. And I think you'll see that today. It's astonishing progress and incredibly inspiring, actually, just to watch engineering on this scale come together. The precision, the size, the complexity on a scale that I think has never been seen before. So thank you, Bernard, for accepting Princeton's invitation to speak to us all. And we're all really looking forward to this seminar. And I will stop talking because everybody wants to hear from you. So Bernard, thank you.
So thank you so much, Steve. I am very pleased and deeply honored to have opportunity to speak to this audience. As you know, your center is dedicated to energy and environment, and I really do believe that fusion power could make a difference in these 2 domains for the long-term future of humankind. It's really a real pleasure to be with you. Indeed, I have foreseen to visit Princeton, but due to the coronavirus crisis, as you could imagine, we need to work only remotely. So you could see on my screen a picture of the ITER work site as it is now. I'm sure you understand that it is a quite large platform, nearly 1 kilometer long, 500 meter large, where at the center you have this big building, nearly 180 meter long, which is what we call the tokamak building, which will host the very hot plasma. I will speak in a few minutes, and also the assembling hall, because we need to pre-assemble the components, which are so large and complex that we could not install them directly in the tokamak building. This project is very large, ambitious, as you said, and so is very challenging. It is why several large partners representing 35 different countries has agreed to join their effort and their resources in order to make it successful. But for each of the 7 partners, including the US, I do believe that this program is a core element of their national program in order to demonstrate that hydrogen fusion could make a big change in the world energy supply, demonstrating the capacity of a burning plasma. So I'm sure you are familiar that the 7 members are China, Europe, India, Japan, Korea, Russian Federation, and the United States, all together working for demonstrating that this first-of-a-kind machine could operate and fulfill its mission. So fusion is not a unique phenomena in the world. It's very, very popular, I would say, because it's power the sun and stars for now billion of years, and we expect it will go on for some other billion of years. The sun and the star indeed are working, as I will explain now, is a huge mass. And at the center of the star, of the sun, you have a huge forces which we call gravitational forces. It's are exerting a very strong pressure on the hydrogen, because all these big stars are indeed largely made of hydrogen, and they will be able to force the hydrogen nuclei to get so close together that they will fuse. It is these phenomena which are powering the stars, as we know now very well. So evidently, for example, the sun is 300,000 times weighing more than the weight of Earth. It is not possible to reproduce it easily like in the star with just the gravitational forces. Is why the physicist has been very bright to imagine something completely different. In the sun and the stars, the density of this hydrogen plasma, as we said, is nearly 100 times the density of steel. So they consider a completely different option, which will be a very low density plasma. The density of the plasma will be a density of 1/1,000,000 the density of the atmosphere. And in this condition, you are able to accelerate the hydrogen nuclei, and when they collide, they will produce 2 new particles. One particle is an helium nuclei, and the other one is a neutrons. And as you see on this slide, when you collide at the right temperature, which is 150 million degrees, 10 times the temperature of the core of the sun, you are producing a huge amount of energy. The energy of the collision is of the order of 0.7 million of electron volt. Doesn't matter the unit, just to remember that when you expel the 2 particles, the helium will go away with 5 times more energy, and the neutrons 20 times more energy. So there is a very large net outcome of energy, production of energy. Just to give you an order, if you fuse 1 gram of hydrogen brands, indeed in this case is deuterium and tritium, 2 special brands, what we call isotopes, it's like if you burn instantaneously 8 tons of oils. So once you have this, okay, two particles, they will collide with the wall of the vessel and they will transfer their kinetic energy because they will be abruptly stopped. They will transfer their kinetic energy to heat. And you will collect the heat, for example, with water to produce a steam, and you will make okay, the steam running a turbine, and you will get electricity. So it is this scheme which is used. Indeed, if I would say this machine will be just a special boiler, okay, boiling water, having steam in order to make the turbine running. Why all these 7 countries are so keen to have this common experience to be done is because fusion are showing very critical advantage. First, as you explained, it is a way to produce massively, okay, power. You could do it continuously. You could also modulate, okay, this production, even stop and go. Okay, so it's very good to have it as a base load energy, which will complement the production of renewable energies, because most of the renewable energy are intermittent. So it's an excellent way to complement it. And it could substitute, for example, most of the burning of oil and gas as we are using now to produce electricity. Second advantage, it is safe. Within the large vacuum vessel, the vacuum vessel for ITER, for example, is over, okay, 1,000 cubic meter. You have only 2 grams of fuels, of hydrogen. So any parameter which are deviating for its okay, nominal values will immediately lead to a stop of the fusion. There is no storage of energy, of heat. There is only a flux of energy. So there could not be any meltdown of the equipment. Third, we are just producing helium, as you see. So it is a non-radioactive, greenhouse gas, and so no impact on the climate and very little impact on environment. We have some impact because we will produce a few radioactive waste coming from the activation of the wall from the neutron collision, for example, or maybe the tritium also. But it is no long-lived high-activity radioactive waste. After maybe a century, okay, we will go back to the natural radioactive dose. And not a small advantage, there is so many hydrogen atoms or precursor of the hydrogen fuel, which are the water and lithium on Earth, that there is enough raw material for millions of years, okay, in order to provide the energy supply of a population of the order of 8 to 10 billion of inhabitants as it is now. So this big event justifies the effort. And this is why, okay, all these countries has requested the ITER to achieve a special mission to demonstrate the industrial scale fusion capability and to be able to have what we call a burning plasma. As I explained to you, we are producing the helium nuclei from the collision of the fusion, and the helium has quite a large amount of energy still. And how could you confine, okay, the plasma? 150 million degrees, as you know, is not easy to handle in any vessel. You will do it by magnetic field. And the big advantage of the magnetic field, it could act at distance and confine the plasma away from the wall. And the second advantage of the magnetic field is that it will accelerate the electrical particle at this temperature. Clearly, the atom does not exist any longer. You have on one side the electron, on the other side the nuclei, and so you have produced electrical particles which will be accelerated by the magnetic field. So it captures the helium, and so the helium will be staying within the plasma before we pump it out. Before we pumping out, it has time to auto-heat, self-heat the plasma. So it's why we call it a burning plasma. And the mission of the ITER is to demonstrate that we will be able to produce 10 times more heat that we feed in the plasma when the plasma is burning, when the plasma is on a steady state. So it is a key ambition, okay, with factors of 10. We will heat with of the order of 50 megawatt of power, and we will get out from the plasma 500 megawatt of thermal energy. So how it works? Indeed, first you have to do the vacuum in the large vessel in order, okay, to eliminate any other atoms than the one you will introduce in. And you will introduce these 2 grams of hydrogen. Immediately you will make an electrical discharge in order to produce in a first step what we call a cold plasma. So it will be just separating the electron from the nuclei of the hydrogen atoms. And because they are embedded in a magnetic cage, they will be accelerated and they will heat and reach a temperature of several million of degrees. But it will not be enough to start the plasma. We need some additional heating system, for example, electromagnetic waves, also injecting some high energy hydrogen atoms in the plasma, and it will heat up, and as soon as it will reach the temperature of the order of 150 million degrees, okay, the plasma will go fusing and we will produce energy. So the big challenge is clearly how could we hold something like 10 times hotter than the core of the sun? And to do that, we do it, as I explained a few minutes ago, with a huge magnetic cage, a giant magnetic cage. I guess you see the size of the man at the bottom of the magnetic cages, okay, even if it's 2 meters. Okay, the cage is have a height which is of the order of 20 meter large, okay, and with several pieces. Indeed, there is 18 vertical coils, what we call toroidal magnets, okay. There is 6 horizontal one, what we call the poloidal magnet. Each of them, as you see, are weighing between 200 and 400 tons. And we have also a central solenoids. Okay, indeed, it is made in the US, and all these pieces, weighing a very large amount of mass, has to be adjusted with a precision which is below millimeter. Why is this? As I explained, the hydrogen nuclei will be circulating. So if the curves of the trajectory is not perfect, okay, the hydrogen nuclei will collide with the wall and the plasma will be stopped. So we have to be very sure that the magnetic line is just precisely positioned, and you have to do it very precisely to avoid there is gaps in these magnetic cages. So it is maybe the most challenging issue we have to resolve, assembling these larger coils with the required precision. The equipment we are now installing is named a tokamak. It is a name indeed in Russian, which means a magnetic torus. We have a torus in order to have this circulating hydrogen nuclei. And indeed, the very early tokamak was what I could call a table tokamak. You could have it on your table. And maybe if you go to Praha in Czechia now, and you go to the Charles University, you will see the first tokamak in the world still running, which is a gift from the Russian to the Czechia, and you could observe some fusion phenomena. But per unit time, you have so little fusion events that it requires much more energy to feed in than you will get out. So the size is absolutely critical. And is why, from different experience, including the TFTR in Princeton, which are now closed, but also, as it has been mentioned, the NSTXU in Princeton, many labs has tried to develop, okay, some, I would say, reduce the size tokamak in order to experience the physics associated with the fusion, okay, hydrogen fusion plasma. K-Star in Korea started, for example, a few years ago, and is working very nicely. And the world record now to deliver, okay, power from fusion is indeed the JET. Okay, Steve has been the director of the JET. He knows very well that equipment, okay, near Oxford, where they have been able to produce 16 megawatt of fusion power, but they have to inject something as 23 megawatt of power, which means that the yield was below 1. So it was nice for having some good experience, but not so good for energy supply, as you could imagine. Size is absolutely critical. You want to have a sufficiently large volume of plasma in such a way that you may have a burning plasma and with sufficient fusion event per unit time. And as I mentioned, the world record is a jet, and you see the volume of the plasma is of the order of 80 cubic meter, while the volume of the plasma of ITER will be 10 times larger. The heating power, as I mentioned, for the jet was of the order of 23 megawatt, and the produced fusion power was 16 megawatt, the yield of the order of 70% only. While the heating power in ITER will be twice, okay, the one in jet of the order of 50 megawatt, we will have a production of fusion power which will be 30 times larger. So the size is absolutely decisive, and it's not just for fun that we have decided to have this large ITER tokamak to be designed and manufactured. It is a precondition to be able to observe, okay, a large outcome of fusion power. So on this screen, you see a cut of the tokamak equipment, tokamak facility. As you know, all these pieces have to be very tightly, okay, interlinked, assembled. You see the cut of the vacuum vessel, the torus. It is the orange parts. It is made of stainless steel. It is of the order of 17 meter high, okay, and 20 meter large. And it is a double wall vessel in such a way that the water will flow in between the two parts of the double wall. And beyond that, we have put some tiles. Okay, there are the blue parts on the left side of the screen, where you have this tile collecting the neutron very efficiently. They are made of, indeed, of beryllium. And at the bottom of the vessel, you see what we call the divertor, where you will pump out the helium, you produce when the hydrogen is fusing, because if you keep the helium in, they will, okay, make the plasma fading and no longer producing good energy. So it is the core piece, and you have to pump out to make, as I said, very, very high vacuum, 10⁻⁶, okay, the atmospheric pressure. Embedded, you have this vacuum vessel is embedded within the magnetic cages. And you see the magnetic cages is made up of the blue magnets. I explained to you a few minutes ago what we call the poloidal and toroidal and the central, okay, coils. And the temperature of this magnet, which are made of superconducting material, has to be cooled down at a temperature of -270 degrees, 4 degrees Celsius above the absolute temperature. And so in order to preserve, okay, the energy, we have put all these pieces in a big box, what we call the cryostat, 30 meter large, 30 meter high, which will be filled with, okay, gaseous helium at -190 degrees. So all these things has to be precisely assembled, as I mentioned. They are representing of the order of 23,000 tons of material, which is equivalent of 3.5, okay, Eiffel Tower weight. We are in France, and I guess everybody understands what is the Eiffel Tower, and we have to put this in this big box there. So it is a challenge we are now facing. How this project has been developed? Indeed, fusion has been observed and considered for the very early years of the 1950, but it is only when these two gentlemen, and maybe you recognize their face, President Reagan from the US and Secretary Gorbachev, met in November 1985 in Geneva, and they decide ending what we call the Cold War, and decide to work together in order to make fusion a reality. And they launch a large international program and invite any other country to join. And during nearly 15 years in San Diego, in California, in the US, in Europe, nearby München at Garching, and also in Japan, in Naka, of the order of 200 engineers and scientists have developed the design of this equipment and demonstrated its feasibility. And around the years 2000, 2001, they consider that the project was mature enough, the design was good enough to start thinking about how to launch the program, and deciding about the governance of the program, deciding about the funding, and deciding about the localization, the site, the sitting. It takes nearly 5 years to have an agreement among all the different stakeholders. And in 2006, in November, there was an agreement between all the parties, and they launched the process. And you see in January 2007, we start deforesting a small piece of France and giving this piece of France to the project. It is no longer a French territory. It is a part of the American territory in France now. You are co-owner of this land now. We start preparing the site, as you see, in August 2010, and you see where we are now with the platform quite busy. As I said, it is a really global challenge to demonstrate that fusion power could be a very good option for part of the energy supply for the long term. And so we need a global response. And it's why, we had this agreement, what we call the ITER, joint agreement. And as Steve has mentioned, now more than 50% of the world population, of the order of 85% of the global world GDP, has mobilized in order to succeed with China, Europe, India, Japan, Korea, Russia, and the US sharing their best expertise and resources to make it successful. They have decided that because this fusion could be really a breakthrough for the world energy supply, they want to train each of the 7 members. They want to train their best industry to demonstrate their capacity to manufacture, design, manufacture some of these very challenging components. Is why, they decide to set up a very integrated structure with the ITER organization, where I am now, having the responsibility to coordinate the whole program. It will be what we call the nuclear operators, in charge of assembling the component and operating the facilities, and 7 domestic agencies, which are in charge to procure the various components and support the project. And you see the share is in-kind value is of the order of 80–90% of the construction phase, and the in cash is of the order 10 and 20%. But it has been agreed from the very beginning that the total developed knowledge, the created intellectual and industrial property, will be fully shared by all members. For example, if the US are developing the central solenoid and Europe is developing the vacuum vessel sectors, they will exchange all the information in such a way that if tomorrow the US want to build a new tokamak, which will be able to improve the performance of the ITER, okay, they will have all the knowledge available. So they have decided in the joint ITER agreement to have a share of the in-kind of the different components to be manufactured by the different countries. Europe has accepted to take a share which will be 5 times larger than the share of the non-European country. The main reason is obvious, is because it is in Europe, so clearly it will create quite a large, significant economical activities in Europe, and so is why Europe have accepted this extra share, but all the others have the same share, 9%. So the US contribute 9% of the value, but the US will have access to 100% of the facility and of the knowledge which has been developed. So it's good leverage, if I could say. So where are we now? We are now, as again explained, when I came in, having a new schedule, very clear program, and we are facing a few challenges. The challenge is we are manufacturing and moving and installing components which are more familiar in a naval construction size, 20 meter large, several hundred of tons. For example, in the ITER assembling hall, we have giant tools which will be able to handle components up to 1,500 tons and position them with a precision which will be below half a centimeter. And at the same time, we need very high precision in the manufacturing. So it's what we call a watch-like precision. And for example, at Mitsubishi Heavy Industry in Japan, they have been able to insert the 300-ton toroidal field magnet into its case with a tolerance of 0.2 millimeter. Why? The superconducting coils are indeed some ceramics, so they are fragile. The magnetic field is huge. It could be up to 5 Tesla, even up to 13 Tesla. So if you are not putting the coils in a case, you will breach the coils. You have to put them very precisely in such a way they could have no mechanical move, which will create the disruption. And I am very proud to say that now we have been able to demonstrate that we are able to manufacture these coils, and 2 of them already arrive on the ITER side. The second challenge we have is the challenge of integration. We need to integrate a lot of different technologies. Clearly, magnetism, but also neutronics, also vacuum, and cryogenics, and so and so. And you see, for example, the complexity of each of the sectors of the vacuum vessel. Indeed, we have divided the vacuum vessel, which is a huge size, in 9 sectors, like a piece of orange, and each of the sectors will be well together after they have been assembled with the coils, the vertical coils. And you see the complexity. There is 100 or 1,000 of pieces to be very precisely assembled. And the third challenge we are facing is when you have so many partners, and indeed one part could be made in one country, going to another one to be assembled, going to a third one, to be completed before it arrives on the site. So it's a huge collaboration with, I don't believe, no equivalent in the world so far. So the project had a little slow start due of a misunderstanding of the challenge and complexity to manage a so large project with 35 different countries. And so in 2015, I was requested to consider to help this project, and I agreed. We have made a thorough review of the project, and we come with a proposal, a new proposal, with a new schedule, with a new cost estimation, and the schedule has been approved with a first plasma, which will be demonstration that the tokamak is properly assembled in December 2025. But at that time, we will not be able to start really physics experiment because we will have not the component to collect the energy. The famous first wall I was speaking about, okay, made of 400 tiles, indeed, with their cooling, okay, water cooling support, and also the thin layer of beryllium. So we will need to assemble these parts, and when, okay, they will be assembled by the end of 2028, we will be able to start physics. And later on, okay, we will install some auxiliary, okay, fusion heating system and the tritium plant able to recycle, okay, the fuel. And by 2035, okay, we will be ready to demonstrate we have a burning plasma producing 10 times more energy that we feed in. It is a very challenging schedule, but you would believe still if the coronavirus let us going to work, it is still feasible. So we have a planning, and as you see, all the big components will arrive in 2020, 2021 before they are completely assembled, commissioned with the first plasma in 2025. And after that, we have what we call a stage approach, a successive sequence of complementary installation, assembling phase, and first physics experiment. And as you see, in December 2028, we expect to be ready to start for what we call the pre-fusion power operation for one, with, for example, only plasma made of hydrogen and helium. And by 2035, it will be with the deuterium and tritium, the most efficient fuel to demonstrate the feasibility. So before terminating this presentation, I want to show you some progress of the project. So it is a crane, driver looking ahead of the tokamak building. You see, during the last 6 years, we have progressed quite well. When in 2014, I considered to take over the Director-General position, it was nearly a green field, 1 kilometer long, as I said, and 500 meter large. And now we are struggling to find the place in order to complete the assembling of the different components. We are monitoring every month the progress we are achieving, and it is a real photo very recently taken in the Provence sky, and we are observing how we are able to achieve nearly 25 different activities needed to go from design to first plasma. And I am pleased to say that recently we go over 70% of the work which is done. And during the last 5 years, we perform around 0.7% per month of progress. And if you think about that, now we are of the order of 70 months to go up to first plasma 2025. 70 multiplied by 0.7, we are on track. But as you could imagine, certainly the assembling is the most critical time, and is why we need some consideration of maybe a slowdown of the progress. Here is a work site. Again, you see in the center what we call the tokamak complex, with the assembly hall behind. You see it's 180 meter long altogether. And we see also the big switch yard, which will be able to power the coils. The coil will be powered with an intensity which is 70,000 amperes, very large. You see also the cryoplant. It will be the largest cryoplant in the world, able to produce and cool down constantly 25 tons of helium at a temperature of minus 270 degrees. And you see also all the other equipment, and the project is very, steadily moving. And as I explained, 2020-2021 will be decisive years with all the arrival on the site of many of the key components, including one of the central piece, which is what we call the central solenoid, and the first central solenoid module among the 7 which is under fabrication in the US will arrive to be assembled. So just a few pictures. Again, you see the tokamak complex in March 2020. Indeed, now the tokamak is ready for equipment. Very recently, we have been able to move the larger crane, which will be able to lift 1,500 tons in position with a very high precision, okay, the component, okay, on time. Recently also we move, and you see with a drone photos, you see the base entering in the assembling hall, and the two other parts of the cryostat base are on the side. You see the big, okay, rings you see which are white on the picture. And we open completely what we call the tokamak pit, which is 40-meter high and 35-meter large, in order to position the cryostat first and after the tokamak. So it's very recent. It's okay, mid-April, but we have been able to do that just on schedule. And you see the cryostat base is now installed in the assembling hall to be equipped and ready for lifting. And we expect that the lifting and positioning will be completed before the end of this month. And you see when the upper cylinder just emerged from the workshop to go into storage very recently again. So many other components are on their way to be completed in order to be commissioned. For example, the heat removal system, because we will produce a lot of heat, as I explained, okay, the steam coming from the tokamak. And so before we flow back the water to the river, we have to, okay, cool down this hot water coming from the secondary circuit of the component. Also, the power supply, the larger switch yard and the magnet power conversion building are now ready. The switch yard is connected to the European, okay, grid. And what we call the bus bar, huge piece of cable able to conduct the high, okay, intensity, is now 99% installed in the magnet power conversion building. The cryogenic plant also is supposed to be commissioned next year. And also we have some pieces which are manufactured on site. For example, we have completed the poloidal fill coil number 5. Okay, it is now done completely. It is nearly 17 meters large and nearly, okay, 300 tons. And it is ready to be installed. And the second coil, the number 2, is in fabrication, as you see. We have received, okay, the first 2 toroidal fill coil fill magnets, as we said, one from Italy, the other one from Japan. And you see, we celebrate this very recently. So we are now moving from fabrication with very strict, okay, specification. As you see, the tolerance in millimeter for pieces which are of the order of 20 meters. And I spoke about the superconducting power line, okay, to assembly preparation. Here is an assembling hall as it is now, with the pit ready for having, okay, the cryostat base you see at the back of the picture to be installed this week. And also we have to, okay, make some mock-up in order to demonstrate how we could weld the 9 vacuum vessel with the appropriate precision with robots. So there is a lot of robotics which is developed. You see, it is an illustration of the complexity of the share with many countries contributing to the same component and to be working all together. The US, for example, is contributing very significantly with some very innovative technologies. For example, we need to inject some pellet, okay, which are frozen piece of, for example, hydrogen or rare gas, and we need to invent in some way this way in order to, what we say, mitigate some disruption in the plasma. The central solenoid, we are naming in the beating heart of ITER, and it will be the most powerful magnet ever built. And also the US are in charge of the tokamak cooling water system with a lot of exchanger, okay, pump, piping, and all these things. You see the complexity of this. Yeah. All these parts are now under manufacturing in the US. For example, for the nuclear piping, it is some companies in Mississippi. The central solenoid modules is in California. Multiple diagnostics are also on its way. Some big, very innovative pumps are now under their manufacturing to be installed on time. You see the complexity of the various contribution of the US, and you see the main one on volume, which are the heat exchangers, but there is also the toroidal field coil conductors, for example, the steady-state electrical network, the ion synchrotron, which is some additional heating systems, and also some diagnostics, very highly innovative technologies. But not only in the US, everywhere in the world, you see all these different components. I just want to focus, for example, on the thermal shield. You have to know that the temperature of the coil will be minus 270 degrees. And a few centimeters away, you will have the vessel, the wall of the vacuum vessel, which will be 200, 250 degrees, more than 500 degrees difference in just a few centimeters. So we need what we call a thermal shield, which will be made of steel. It is plated with silver, and this part is coming from Korea. And I name it the jewel, because this is reflecting a lot of the light as a diamond could do it. And also you see the divertor cassette prototype. It is a piece which will collect the helium. You see the size with a real man, manufacturing them. 54 of these divertor cassette will be produced and will be installed by robotics. All of us in the world are moving on just to illustrate how intensively all the partners are working to deliver their component, including this one. It is the first vacuum vessel sectors which is now ready for shipment. You see the complexity and the size. It took nearly 6 years to manufacture the first one with very high specification. And now with the lesson learned, we expect we will have all of them on time. All these pieces are coming from China, Korea, US, Russia, and so and so. Usually they are traveling on ship and they are crossing the ocean, and they are coming on either side through the road. And very recently we had some of these pieces you see arriving on site. It takes 4 nights at the speed of 5 kilometers per hour in order to arrive on the other side. And you see how numerous highly exceptional load convoy we have to manage. A lot of impact on the economy so far. There is more than 9.5 billion euro in contract for construction and installation all over the world. We have also quite a large number of very talented, very skilled and experienced people working on either side, beyond the one which are working in the domestic agencies and within the suppliers. And you see, we have this share. Indeed, initially it was considered that the share of the IO staff has to be the same share as the value of the contribution in kind. But before it was like a UN project. Everybody has his right to have 9% and the other 45%. But indeed, it was not the best way to attract the most talented fellow. So when I came in, I say, I just want the best talented and motivated people. So just on quality. And unfortunately, as you see, Europe, due to the proximity, is faring much better. The US, there is a lot of possibility for the US to have more. You could double the number of people. Right now, we have nearly 50 people coming from the US. We will be very pleased to welcome doubling this number. So yes, there is a lot of room for any of you if you are willing to join us. Just to conclude, a lot of innovation. For example, here is some robotics in order to weld some of the coils. Also we have explosive forming, signal transmission, very high powerful system. just to conclude that this project is indeed the project of each of the 7 members. And ITER has been fully recognized as a core element of the US fusion program, research program. It has been recognized by the National Academy in 2 reports. And very recently, it has been recognized also as a key gate for burning plasma with the Community Plan for Fusion Energy and Discovery Plasma Science, which has been published this year. And PPL has been contributing, and we are very grateful for this very good paper. So good value for the US, clearly the promise of fusion energy to be demonstrated with a good leverage, because I explained 9% investment, but 100% capacity to reward, and expanding industrial capacity due to this very innovative challenge to manufacture this component, and including with some spin-off. And you see all over the US, many companies have been contributing so far, and we expect that more could do, as you see everywhere in the US. So I guess I am just on time to thank you very much for your attention. I wish you maybe be interested by fusion and consider that it is something which is worth to try, because if we succeed and we do everything we can in order to succeed, it will be a real breakthrough for the world, for the humankind, because it will supply energy safely without any impact on environment and climate. And I do believe that more and more people are aware that it is something we need. Thank you so much for your kind attention.
Well, thank you, Dr. Bigot. Thank you very much. That was a great presentation. For those of you who didn't get the message on the chat board, we have a Q&A button, and if you can put your questions there, I'll read that out to Dr. Bigot, and he will be able to answer them. Sorry, we can't get people all in to show their faces. We have too many people, and I don't think we can do that. First, I want to give Steve Cowley, if he has any questions to start with.
When will we see the toroidal field, the first toroidal field core going in, the first sector going in?
Okay, so the first sector, will be normally installed this summer. Okay, we expect that the 2 coils, which have to be assembled, will be by the end of June there. The vacuum vessel will be on June also, and we will start the assembly. So we expect that in the tokamak, we will have this coil ready by this summer.
Oh, that's wonderful. Yeah, great yes, progress.
Very challenging, as you could imagine, but we are ready. All the big companies which are supposed to install this equipment, they are now their people on site, and they are training themselves, in order to demonstrate that they will be ready to cope with the challenge.
Thank you so much.
Dr. Bigot, there's a lot of questions about COVID-19 and how you're able to get ITER production manufacturing going during this time of crisis. And I see you made a lot of progress. So maybe if you can expand upon that a bit, it would help other people, like, at PPL, we're trying to build NSTX upgrade. Other people then are Commonwealth, and some other private companies are trying to build their machines. Maybe you can give us some clues about how you're able to continue.
So, we have 35 different countries. And the coronavirus, we were exposed to the coronavirus very early, because all our colleagues in China, and there is some manufacturers in Hunan, for example, in December, start alerting us that the coronavirus spread. And at that time, not so many people believe that the coronavirus could hit, the whole world. But we consider it could be, a threat for us. So we decide to set up immediately very strong, precautionary sanitary measure for the people working on the work site, as well as for the suppliers everywhere in the world. Clearly, it slowed down, our activities, but we have been able to keep on all the activities. And I would say ITER is gifted. is nearly what I call a ITER miracle. Okay, even if in some country where they have a lockdown and all these things, discussing with the government, discussing with the CEO of the top companies, they have opened again their manufactory, okay, shop, their workshop, to complete the piece we need in order not to block the whole project. So it is something we are gifted enough to have very strongly motivated people. Why? The reason is the following. There is so many pieces to be assembled. If we stop completely, okay, to restart, it will be very long. So we decide to keep continuity activity. And I am pleased to say, while now the coronavirus in a little bit reducing, okay, we see a very sharp restart. So just follow the precautionary sanitary measure. All our workers on the site are equipped with a mask, a face mask. Okay, we change the mask several times in the day if it is necessary in order to eliminate the risk of propagation of the virus. And I am pleased to say that from the very beginning, indeed from mid-February, when we have been hit by largely by the impact in China, we have not experienced a single infected fellow on the work site.
That's great. That's great. That's really great to hear that. There's a lot of questions about the timeline, and a lot of people are worried about the climate change and the urgency of the matter. And they want to, all of us obviously want to see fusion make an impact on that. Can you talk a bit about how ITER itself, ITER is mainly a scientific project, but how ITER can help in fighting the global warming in a timely manner, and what is the path for that?
It would have been much better to maybe start this program 10 or 15 years ago, certainly in order to cope in the most timely way with the challenge of the climate change and environment concern. But unfortunately, as you understand, it is very challenging to have all these 7 large parties, ITER members, fully aligned on a program, accepting common rules. So it takes time for negotiation and setting the whole project. Now, what is our schedule, I would say? We could not go faster. As I explained to you, some of the pieces are very challenging. Could you imagine, for example, for the first vacuum vessel sectors, there is more than 1,300 meters of welding. And each piece of welding has to be tested because it is a vacuum vessel. And I don't want any leak. If there is a leak, the gas will enter in and the plasma will not work. So it is very, very strict specification. You could not, speed up the process. You could not have, 100 of welders welding on the same parts. So there is a limit on the capacity of the schedule. We expect to have the first plasma 2025. As I explained, first physics experiment 2028. After that, we will have the full fusion power by 2035. I don't believe we will be able to gain a lot of time, even if we got much more resources. We have to go stepwise. It is the best way to learn and to be sure that we will be successful. After that, I consider that we will have to operate during 5 years to make a clear demonstration that fusion works and attract the utilities. If by 2035, 2036, we demonstrate that we are producing 10 times more energy, and maybe we could go even higher, than that, I guess the utilities for producing power will be interested. So we will start partnership, and maybe during the next 5 years, we will work with them to optimize the industrial way to operate. And I hope that by 2040, some utility will start really considering to build some of this equipment. And after that, it will be up to them to demonstrate, maybe 10 years, it will be a reduced time, and by mid of this century, we will have, I hope very much, fusion available, okay, to the planet. Now you could tell me that, okay, the climate change could not wait for that. You're right. In the meantime, we try to have some alternate option, okay, reduce greenhouse gas and so and so. But all this is quite complex. Even, for example, if we develop very largely the renewable energies, as you know, it's quite a large okay, difficulty to connect big grids and all these things. So we expect that it will be a real alternate in order to cope on the long term, on a sustainable way, during the second part of this century, the world energy supply. I know everybody could be impatient, but I don't believe we are working nearly day and night, and it is very difficult, okay, to speed up.
Yeah, thank you for the frank answer there. I have there's a lot of students that are asking a more question about how they can get involved with ITER. I mean, we're talking about a long-term project here, and we have to start training people, get them involved. And it seems like people don't know how to really, you know, start on the path towards, you know, maybe running ITER in, you know, 10, 20 years and getting involved in that. Is there any opportunities for young people other than the national programs? Thank you.
Okay, so we have now a program which is named, okay, the ITER Fellow, okay, Scientist Fellow Network, okay, where we associate, okay, universities and national labs in order to work on ITER program already, okay? So it is a possibility to stay in your national labs or in a university and start working for ITER. We have also a postdoctoral fellow program, okay, with people which are working on the side. We are very aware that this project, even if now it is more an industrial project with good okay, scientific support, we are working for the scientists. And so we have to think about that the young fellow, which are now 25 years, by 2035, okay, they will be 15 years more. They will be on the age of the 40s. And it is precisely when we will need them to take over the responsibility to operate ITER. So it's why we have a very clear program. And if they want, they could, okay, send us, okay, an email, okay, everybody could go on the ITER site. I will not give my email because otherwise I will be overflow very rapidly, but I will do it. But it is something which amazes me. I receive a lot of email from a lot of students questioning exactly what you say. And every week I pick up one and I offer him to have a personal discussion with me to explain what he is willing to do and how he has to be prepared. And you have to consider that ITER is not just fusion expert. We need, okay, scientists in cryogenics, neutronics, materials, okay, okay, IT, and all these things. So there is a very broad spectrum of activities, but clearly you have to prepare yourself, okay, in order to be able to cope with the challenge of ITER.
Thank you. Yeah, we need a big group of people, and it kind of needs to start now to ramp up to the level so that when ITER starts operating, we can have all these people from all over the world coming to France. One question that pops up, many people are asking, is about alternatives. There's, you know, Stellarators and other private companies are going on different routes of fusion. How I know a bit about this, but can you explain how these companies and other approaches can learn from ITER, like from the project itself, from the construction and all that sort of information? Is there a path for these companies to basically bootstrap on what's already been done at ITER?
So first, I am very pleased to see that there is many other okay, projects starting, including, okay, small startup companies with a lot of good private support in the US, for example, in the UK. It's clearly demonstrated that these people feel that fusion could be an option. Clearly, they are not able to build a so large project as the one we are now, okay, developing it, which is for me a precondition in order to have a large outcome of fusion power compared to the input you do. But all these small projects are for me very worthful, okay, very worth, okay, because they are exploring some alternate option, okay, demonstrating some specific parts which could be very useful. Now, how they could benefit from ITER? As I explained to you, all the knowledge, okay, we are now developing is made available for any national labs and any companies of the ITER members which are willing to, okay, benefit from the ITER. For example, I received some requests recently to provide what type of material we are using, what is the standard of the composition of the steel, stainless steel. As you could imagine, maybe, okay, it has to be very pure, okay, to avoid to be activated or to have some magnetics, okay, counter effect and all these things. So we are ready to provide it is for developing activities, not yet commercial activities. But none of these programs are yet commercial. They are trying to make good demonstration. So any of these projects, and we are interacting with them, are welcome in order for us to share the know-how we are. I am frank with you. These projects are now 12 years of experience. And I am pretty sure that the next tokamak we will do much better. We have learned a lot already on manufacturing, on, okay, standard we are using, on process. So all this is fully open to any of these small companies.
Thank you. So I would like to know, basically what you're saying is that this is the knowledge that ITER produces helps all the other companies as well, and all the other approaches. This is all
Yes.
public,
Yes.
is shared with all the companies. And are the scientists able to collaborate with other companies and other institutes outside of ITER?
Yes, yes, absolutely. Yes, no limits on that.
Great. I don't know if we have too much time left here, but so there's a lot of questions about safety, maybe just a general nuclear safety and disruptions, you know, about all these issues. And if you can maybe talk a bit about how ITER is taking the general safety of the fusion reaction and of the plant. What is the path you're taking? I mean, these kind of things come across when we talk about the autonomous vehicle safety, all these complicated systems. You have to have some sort of a safety approach. Can you talk a bit about that?
Certainly. As you know, okay, we will produce a lot of neutrons. Okay, it will be billion of neutrons per, okay, second we will produce. Never been produced before. And they are very energetic neutrons. So you could not have them, okay, going freely in the environment. So it's why we need to have this large tokamak building. And so we are very serious about the nuclear safety, and why it has been agreed by the 7 members that we will just use and accept all the same safety regulation. Okay, it is the French regulation which has been selected, and so it's quite good. It's okay. We from the scratch we decide to have all the same safety standard. Okay, it's not like for the fission nuclear power plant or even for the early stage for the aeronautics, where they have to decide after the fact to have some common rules. We start with the common rules. So the safety. There is, as I said, no risk of runaway, but it does not mean that you have not to protect, okay, when you have the plasma burning, okay, all the environment. And is why we have, okay, very big shielding. As you see, for example, the tokamak pit, this big cylinder you saw on the picture with all the windows, is to collect the neutron. So the first wall with the beryllium will collect maybe 99% of the neutrons, but the 0.9%, okay, it will escape, and we have to, okay, stop them with the bioshield wall, and it works properly. So you have to know that when we will run, okay, the ITER, okay, facility with the hot plasma, okay, the radioactivity which will be created in the vicinity, in the neighborhood, will be, okay, only 1% of the natural radioactivity in France. Very little, okay. In the worst case, if we have an accident, for example, the vacuum vessel break apart, and so you could have some release of this, okay, as I say, short-lived radioactive material or of the tritium, okay, it will be, okay, only the standard, okay, radioactivity in France. No need for having people to flow away from the neighborhood. So it's a really safe, okay, technologies. We have certainly to maintain and respect the nuclear regulation, but it is not okay, difficult. Very often I have questions which say, could we expect to have fusion in a car or in aerospace and so? My answer is very clearly no, okay, due to this constraint of confinement of the neutrons. You could not expect to have a big shielding, okay, of your car in order to protect the neutrons. And second, the size is critical. You will benefit from the electricity, but not directly from the fusion power.
Thank you. I think we are way over time. This was a great presentation, especially seeing the latest developments that you're still able to continue the ITER progress during the virus situation given. And we have way more questions, but I think I try to do the best to group them together. And thank you very much again for having this great webinar with us. Thank you for joining us.
Much. And I wish you, okay, when the coronavirus will be away, to come and visit ITER site in Provence. And so you will see firsthand where we are now working.
Great, that would be great. Thank you very much, everyone. And that will be the end.
Thank you, Bernard.
And thank you.
Thank you.